Okay, so we now know how a multi-cycle data path works or operates. How about the control? As we have said, the opcode and func are not enough to determine the control signals, as we must also consider what clock cycle we are in the execution. Thus, we need to answer, how do we make control signal values that change with clock cycle? Also, how do we make a series of control signals for varying number of clock cycles, sometimes 2, sometimes 3, sometimes 4 clock cycles, and so on. To help us answer this question, we compile first the necessary control signals per clock cycle to serve as our guide. Let's start with a more manageable set of instructions and consider the 4 R-type instructions only, the add, sub, and OR. Let's say that the control unit takes on a quote-unquote state for every clock cycle in the instruction execution. The first state, let's call it state A1, is for PC update and instruction fetch. Let's call the second state for the second clock cycle as A2, where we fetch the register operands. Next, the control unit will take on some state R3 for the third clock cycle, where the ALU performs the operation. And lastly, state R4 for the fourth clock cycle, where we feed and write the result to the register file. Now, if we are considering or expecting only R-type instructions, then the next instruction must also be an R-type instruction, and our control unit must loop through these 4 states. Note that states A1 and A2 are similar to the first 2 clock cycles of other instructions. That's why we named them as such, where A stands for all. Now we proceed by filling up this table of control signals for different states or clock cycles. Let's go with the per control signal basis. First, we write only to the PC and IR at the first clock cycle, so write PC and write IR must only be 1 only at state A1. Next, for R-type instructions, we use the second register operand and not the immediate, so cell of B must be 0. However, this only matters on the third clock cycle. Next, we must provide the correct ALU op at the third clock cycle. However, its value changes depending on the funct value, so let's just indicate that as some function of funct f_funct. On the other clock cycles, the value of ALU op is a don't care. Next, let's jump to write RF. We know that writing occurs only on the fourth clock cycle, so we assert only write RF during R4. However, we must ensure that no unwanted writes happen, so we indicate 0 for states A1 to R3. Now, since we have already deasserted the write RF signal on the first 3 clock cycles, then whatever we feed into the write ports of the register file will not matter. Thus, we can write X for cell data and cell dest for the first 3 clock cycles. However, for the fourth clock cycle, we must ensure that the destination is RD, so cell dest must be 1, while the result is from the ALU, so cell data must be 0. For R-type instructions, write mem must be 0 throughout. Now, since we are writing only to the PC at the first clock cycle, then cell PC increment and cell jump are both don't cares for states A2 to R4. For the first clock cycle, we must increment PC by 4, so cell PC increment must be 0 and cell jump must be 0. And by this point, we have already completed our partial control signal table for R-type instructions. Here we have the first 4 identified states for R-type instructions. We then proceed by including the states for other instructions, starting with add I. For add I, cycles 1 and 2 are the same with R-type. Cycle 4 is also the same, where we write from ALU reg to the register file. The only difference is the third clock cycle, where we use the sign extended immediate instead of the second register operand. Thus, we add this new state at the third clock cycle, which we will call I3. Next, we consider store word and load word instructions. Again, cycles 1 and 2 are the same with R-type. Although this time, we note that cycle 3 of store word and load word is the same as that for add I, where the sum of rs and the sign extended immediate is saved in ALU reg. From this onwards, the store word and load word instructions differ, so we introduce these new states S4, L4, and L5. Note that the state I3 is shared by add I, store word, and load word. Also, note that in our data path, store word executes in 4 clock cycles, while load word executes in 5 clock cycles. Next, BEQ and BNE still follow the same steps for cycles 1 and 2, but differ in the 3rd clock cycle, where a write to PC may occur depending on the 0 flag. Thus, we introduce new states B3 and N3 for BEQ and BNE respectively. Lastly, the jump instruction is the same for the rest of the instructions for the 1st clock cycle. However, even if the 2nd clock cycle differ for jump because of the possibility of a jump, we can simply adjust the 2nd clock cycle to accommodate this possibility. To further justify this approach, the processor will not yet be able to determine that the instruction is a jump instruction at state A1 since the control unit only starts decoding the instruction at the 2nd clock cycle. Thus, it will only know that the instruction is a jump starting at A2. Lastly, we add these connections to enable the control unit to go back to the initial state and start at A1 when executing the next instruction. We will use this table to summarize the control signals for all states we have defined with notable values highlighted in red. First, the instruction register, IR, is written only at the first state A1 after fetching the instruction from the instruction memory, and the instruction code stored at the IR must be maintained at the other states. Next, the PC is always written to at state A1 but can also be written at state A2 if the instruction is a jump, or at states B3 and N3 depending on the value of the 0 flag. For branch if equal at B3, we branch if the 0 flag is asserted, so we write that as Z. For branch if not equal at N3, we branch if the 0 flag is deasserted, so we write that as Z prime. For select PC increment and select jump, note that for all cases where write PC is 0, then these two rightmost control signals are don't cares. At the first clock cycle, A1, cell PC increment and cell jump are both 0 to increment the PC by 4. At state A2, cell jump is asserted only if the instruction is a jump to select the jump target address. In this case, the select PC increment is becomes a don't care since the jump address will be selected either way. For B3 and N3, select PC increment is 1 to select the offset. And since the other multiplexer acts like a gateway, then cell jump must be defined and given a value of 0. For the next control signals, cell of B must be 0 at R3 to select the second register operand for R-type instructions. Cell of B must be 1 for I3 to select the immediate for add I, load word, and store word. But for B3 and N3, cell of B must be 0 to select the second register which must be subtracted from the first register to perform the comparison. For ALU op, its value depends on the function. For R-type instructions at R3, it must be an add instruction. For I3, for add I, load word, and store word, and must be a subtraction for B3 and N3 for comparison of operands. Cell data is 0 for R4 to select the result from the ALU, but is 1 for L5 to select the fetched data from the memory. For celldest, since the last states for R-type and add-I instructions are merged at R4, but with R-type instructions writing into RD and add-I instruction writing into RT, then we can write the entry for celldest to be some logic if R-type, so that RD is used for R-type instructions and RT otherwise. For load word at state L5, the destination must be RT, so we write 0 for celldest. We write only into the register file at states R4 and L5, and we write into the memory only at state S4 for the load word. Or sorry, the store word. Now in this big table, note that all write enable signals, write PC, write IR, write RF, and write mem are always defined. Okay? And never a don't care to prevent unwanted writes to happen, while the other control signals for multiplexers and the ALU can be don't cares whenever they are not important or are not used. Now that we know the control signals for each instruction, for each cycle, or for each state, the next question is, how do we generate these signals? Given the behavior expected, we proceed and say that the controller can be implemented as a finite state machine or FSM. An FSM is one where we have known finite states and where we have known state transitions and outputs. In this case, our outputs are the control signals based on the states and the inputs, which are the opcode, function, zero flag, and so on. In a finite state machine, we can use flip-flops to hold state information and then use combinational logic to determine the outputs and the next state. Thus, the general structure of a finite state machine should look like the one shown. Here we see that we have an output logic block and a next state logic block whose outputs depend not only on the input but also on the current state. But before designing the output and the next state logic blocks, we must first specify how we want to store the state in our flip-flops. There were 10 states in our previously shown state transition diagram and also in our table, whereas we have multiple output control signals. There are different possible implementations on how we can hold state information using flip-flops. The first one is where we use the list numbers of state flip-flops, which in this case is 4. Using 3 flip-flops will not be enough as it will only result in 2 raised to 3 or 8 possible permutations, which is less than our required 10 states. However, using the least number of flip-flops in a complex system, such as our control unit, will usually result in a complex logic expression and thus hardware for both the next state and output logic blocks. Another possible approach is to use one flip-flop per state, in this approach called one-hot encoding. In one-hot encoding, only one flip-flop must be asserted at any given cycle to indicate what is the current state. In our system with 10 possible states, we will need 10 flip-flops for this approach, which is more than 4. But we'll be able to show that the logic implementation with one-hot encoding will be much simpler. Again, in one-hot encoding, strictly one and only one flip-flop must be asserted at any given cycle to indicate the current state. The single one is made to propagate from one flip-flop to another as the FSM changes states. This is shown in our example below, where the one is being passed from one flip-flop to the next every clock cycle. However, to ensure proper operation, the flip-flop for the initial state must be given the active one on a reset or startup. In our case, we must make sure that before we start operation, the state for flip-flop for A1 must have a value or must have the lone 1. The one-hot encoding state machine for our multi-cycle implementation must be the one shown on the right. Note that we have one flip-flop for each of the states. From A1, the next state is always A2. So we just connect the Q output of A1 to the D input of A2. From A2, only one among B3, N3, R3, I3, and I1 must be set on the next clock cycle. One way to do this is to generate signals R, I, S, L, B, N, and J, which are asserted when the instruction is an R-type, add I, store word, load word, BEQ, BNE, and jump respectively. Since the instruction can only be one among those mentioned, then only one among these new variables must be asserted at any given time. The logic for decoding the instruction code to generate these signals R, I, S, L, etc. must be included within the control unit. From the state transition diagram, we can construct this hardware if we look at when each state becomes active. For example, we go to A2 or give A2 a value of 1 only if we are from A1. Thus, we simply need to connect the D input of A2 to the Q output of A1. For another example, we go to B3 only if we are from A2 and the instruction is a BAQ. The logic expression for this is A2 and B, which we connect to the input of flip-flop B3. For R4, we go to R4 only when we are from R3 or when we are from I3 and the instruction is add, or rather add I. To give an example how to generate the R, I, S, L, etc. signals, consider the opcode for store words, which is 101011. Recall that the opcode is the MSB of the instruction code, specifically bits 31 down to 26. Thus, an appropriate logic for store word or for S is the one shown. Instruction 31, instruction 30 prime, instruction 29, instruction 28 prime, instruction 27, instruction 26, all added or all ANDed. When any of these 6 bits is incorrect, the signal S will automatically be deasserted. Note that the hardware shown includes already the state flip-flops and the next state logic. The only thing missing now in our FSM is the output logic block. For our control signal output logic, we will use the table of control signals as our basis. Note that since we are using one-hot encoding with 10 states, then we have 10 state variables, and writing K-maps with 10 or more variables, including other signals, will be very large. Also, a lot of input permutations will never occur since there must be only one 1 in a one-hot encoding FSM. Thus, we just proceed by simple inspection of the control signal table. Note that the table shown in this slide is smaller since we removed some of the columns and included only a few control signals. In identifying the logic for the control signals, our main variables are the states A1, A2, R3, etc., and the instruction identifiers R, S, L, etc., which are determined from the instruction code. For example, if we consider write IR, obviously the expression for this is simply A1, since write IR is only asserted when the state is A1. Next, if we consider cell of B, the expression can simply be written as I3, since cell of B is asserted only when the state is I3. Next, for cell data, the expression is simply L5, since again, cell data is asserted only when the state is L5. Now, going for a more challenging one, what should be the expression for write PC? The answer is A1 or A2 and J or B3 and Z or N3 and Z prime. We can thus say that the output expressions are relatively simple and straightforward to determine with one-hot encoding. Our multi-cycle processor with the data path and control unit must look like this. The instruction store.ir is fed to the control unit along with the zero flag. Within the control unit is the the state registers, the next state logic, and the output logic to complete the FSM. Aside from the state signals A1, A2, R3, R4, etc., the instruction identifier signals are also generated based on the opcode. With this setup, the control unit is able to generate the control signals that change with clock cycle. We will end this section for multi-cycle control by noting the following. The multi-cycle control is implemented as some finite state machine which depends on both instruction, other signals such as the zero flag and the function, and the current state. The states are stored in flip-flops and need some next state logic to change values. The implementation of the control unit FSM is dependent on how the data path is divided. Using different divisions or definition of states would need a different control unit design. Also, similar execution stages lead to similar or shared states and easier implementation. Aside from the first two states in our example, we were also able to merge the last state for R-type instructions in add-I. We also used a shared state for the third clock cycle for add-I, store word, and load word.